let me go ahead and clear the board. I want to write this. I'm going to write this down one more time. If you understand this, just bear with me, but I think we need to review this a little bit more. Okay. Why don't you go ahead and pass back the quizzes to Aaron. Aaron, if you collect all those for me, and then when you get them all, just set them right here. Okay? All right. I'm going to walk through this. I'm going to walk through this and use the solving diagram that we've been using in class to solve this question. Yes, sir. You may. Yes, ma'am.
What's their grade if they got shoved?
Don't worry about it.
I messed up. I didn't put the subscript 2 in the first molecule.
Mhm.
Put a 3 in front of it, 2. That's what I did because I didn't see the subscript 2.
Okay.
Oh, no.
So by not seeing that right there, right? And so you did this. Okay, now, so you've tried to balance the oxygen, but let's look at the oxygens. Even if you didn't see the subscript there, right? Here you would have 2 sets of 1, and here you have 3 sets of 2, which is 2, it's 6, and so there's 8 oxygens altogether, right? Now look over on the product side. You've got 2 sets of 3, which equals 6, so it's not balanced. Even if you didn't see the subscript, what you didn't look at was the oxygen in this molecule altogether. You didn't include this oxygen. It's almost as if the nitrate oxygen didn't count because it was already nitrogenized. Okay? Okay. But with the equation being balanced, if you recognize this as being a balanced equation, just for process, because this is fundamental. I mean, you're not only you're not going to do well on any of the quizzes, you're not going to do well on the exam either. And this is half of this. This is more than half of this quarter, and this is fundamental to the rest of chemistry. Okay, so everything has built up to this, and everything past this is an application of this. So you have to get this. So using the solving technique we've been using, if we're trying to figure out how many moles of each of these, whatever the number of moles we have here, we're going to move across. In this case, let's go ahead and put oxygen first. To go from moles of NaNO3, the sodium nitrate, to the moles of oxygen, whatever they are, no matter what, I told you I wanted to pick a number, any number, right? Just whatever you have in your mind. Wow, if you want to make that much sodium nitrate, that many moles of sodium nitrate, how many moles of oxygen do you need? Remember the multiplier here? We take the stoichiometric coefficients. It's a 1 to 2. The 1 comes from the implied 1 in front of the oxygen. The 2 comes from the 2 in front of our product that we're comparing, these two things. And since we're moving from right to left, our multiple becomes a multiple of 1/2. 1/2. Since that's true in all cases, it's also true in our balanced equation, right? So a quick check is to look back at the equation and say, okay, I'm saying multiply it by 1/2. If I take 2 and I multiply it by 1/2, what do I get? 1. Is that what I have over here? Yes. Because based on this equation, it's true every time this equation is run. So it definitely works whenever the balanced equation runs, right? When this base equation runs. So you can check it real quick. So there's 1/2 as many moles of oxygen as there is sodium nitrate. And in the same way, going from sodium nitrate over to sodium nitrite, moles of NaNO3 to moles of NaNO2. What is my relationship between the two? Again, I just go back to the balanced equation, stoichiometric coefficients. 2 to 2. The relationship then is to be a multiplier of 1. In other words, it's the same amount. Check our equation. Check this relationship based upon our base equation, our balanced stoichiometric coefficients. the coefficients, the stoichiometric coefficients in our balanced reaction equation. Okay. Moles here is 2. If I multiply that by 1, it should be 2. It is. So it checks. So now that I know that relationship, I can put any number over here. If I said, for example, I want to make 1,000 moles of sodium nitrate, I can look at this right now and say, okay, then I need 1,000 moles of sodium nitrate. And I need 500 moles of oxygen gas. How do you know? Because this is the balanced equation. This is the perfect recipe. This is going to run. And whatever amount I'm trying to make, I need half as much oxygen and the same amount of sodium nitrate. In this case, we just happen to put in 45.0 moles and produce 22.5, and in this case, 45.0. Okay? Any questions on process? Because what we're working with now, the unit section we're on right now, is adding the component of mass relationship to it. So remember, this whole lateral movement back and forth is relating moles to moles based upon mole ratios. The vertical component in our solving diagram is using the molar masses. And I'm hesitant to write it underneath a reaction equation with stoichiometric coefficients in it. So if you can imagine, here's our balanced reaction equation. Okay? Whatever. No matter what it is, it's something, right? If I'm given moles here, and I want to convert to moles here, I need some kind of stoichiometric relationship here with A's and B's, right? This is just a generic write-up. Matter of fact, this might be a good quiz too. Just generically fill in the diagram, because if you can fill in the diagram, you understand process, and if you understand process, then I can give you a couple numbers and you just plug it in, and there we go. Okay? So there's a certain amount of this squiggly line and one of this squiggly line, and then a certain number of that squiggly line. I want to convert from moles of my product to this mole of this reactant, and they relate to each other in a relationship of A to B. So I'm going to multiply by what? A divided by B. This provides me my mole ratio, and my mole ratio tells me whenever I have this many moles of product, I'm going to need this many moles of this reactant. Now, whenever I'm moving up and down, what I'll do is I'll put them both under here, because I don't want you to get confused in thinking that sometimes we multiply by a molar mass and sometimes we divide by a molar mass based upon where it is in the equation. That's not what's taking place here. What's taking place here is whenever we move down from mass to moles, whenever we move down from mass to moles, right? We're going to take the mass divided by the molar mass. It's not because it's in the front here. Let's say we're moving from this to this. We don't multiply, or we don't divide by molar mass because it's on the reactant side. We divide by molar mass because we're moving from mass to moles. Actually, in this equation here, however, we're assuming that we're going from moles of product to moles of reactant. And if we were asked anything about mass, we'd be moving from moles of reactant to mass of reactant. You see that? So we would be moving from moles to mass. We'd be moving up. And as we move from moles to mass, we multiply by the molar mass. So moving up, we multiply by the molar mass. Moving down, we divide by the molar mass. So in this case, from moles to moles, and then if I want to solve in terms of mass, then I would multiply by the molar mass. And the molar mass of what? What molar mass do I need? The molar mass of this reactant that I'm considering. Just as if I were giving a certain amount of mass of product that I wanted to produce, and I were bringing it down, we would then take that number and divide by the molar mass. What molar mass? The molar mass of the product that we're considering. Because we're taking that mass, converting to moles, taking that number of moles, and relating it to another unit of moles for another product or reactant in the equation. And then from that number of moles, converting it back into mass for that specific molecule or element in the reaction equation. Okay? So just like before we use the molar bridge, moles is the center. Moles is the common thing that holds it all together. In stoichiometry, we can only do pure stoichiometry like this with moles. Moles is what provides us the relationship. However, we do have to consider the masses, right? And to go from moles to mass and from mass to moles, we said that the translation here is the molar mass. When we go from moles to mass, right, we multiply. And we go from mass to moles, we divide by the molar mass. Do you see on this diagram here that these lateral movements here in our bridge diagram are the same relationships as the vertical on our solving diagram for stoichiometric equations? Okay? From mass to moles, we divide. From moles to mass, we multiply. It's the same relationship, just depicted a little bit differently. We talked about before over here, if you remember, this is the count. And the translation unit there is Avogadro's number. And if we draw the arrows in the same ways, the operations are reversed. Right? If you rather than using this method, if what you did was always wrote down the statements of equality, relating moles to moles as statements of equality, and created your own conversion factors, you would eventually have to apply this logic when we're given grams or asked for grams. All this diagram does is make it in a very visual process to follow. Hey, I've given this, I'm solving for this. Go from what you've been given, whether mass or moles, to whatever you're asked for, either moles or mass. Stop when your answer is for the right molecule in the right units. Okay? Don't worry, there will be other opportunities. I think our next problem is the glucose problem. Let me get on the right PowerPoint slide and we'll pick it up. Yes. Just right here. That's fine. And I will make it bigger before I even project it. How's that? All right. Let's give this one a consideration. This in your book is example 8.7. 8.7 actually has two different parts to it. This is the first part on example 8.7. Let me go ahead and read the problem to you. Those of you that have module 3, you can follow along either in the book or just listen up. And here it goes. It says, the human body produces the energy it requires to live by burning simple sugars such as C6H12O6. This is glucose, okay? It burns glucose according to the following reaction. Glucose plus 6 oxygen molecules react to produce 6 carbon dioxide molecules and 6 water molecules. This reaction requires a lot of heat, which is used to power all of the body's motion. When the sugar is burned, again, that's what we're seeing here, right? A lot of heat being added to a carbon, hydrogen, oxygen chain in oxygen to produce carbon dioxide and water. Complete combustion reaction, that's all it is. If I said, write the complete combustion reaction for glucose, this is what you would do. The difference being, we write it down like this and we can do that in the lab, but this is taking place in your body all the time. This is a chemical reaction that's keeping you alive, going on right now. If it stops, you die. Okay? When the sugar is burned, the carbon dioxide produced is exhaled, while the water produced is eliminated through your urine. Okay? So when you pee, that's where that's coming from. And when you breathe out your carbon dioxide, when the people beside you smell your pastrami breath, it's mixed with the carbon dioxide right there. All right? So if the average adult human burns about 1.2 kilograms of simple sugar every day, in excess oxygen, again, this is my technique, but I encourage you to do it. It works for me, which means it's right. No, it just means that's the way I remember, okay? I remember it, so I write down my mass of this molecule and told I've got excess oxygen. If your body suddenly says, hey, I don't have enough oxygen, what happens? Your respiration rate increases, right? Your body automatically reacts by breathing harder and bringing more oxygen in. When you're working out, in order to avoid going anaerobic, your heart rate goes up, right, to power the motion, but then your respiration goes up to accompany it. If your breathing never went up, you would move into incomplete combustion and your body would start whacking out, okay? So to keep sufficient oxygen for this reaction, your respiration rate increases. You start breathing heavier and faster. Okay. So the simple sugars are burned in excess oxygen. How many grams of water does the average person eliminate every day as a result of this process? Okay. Again, it's in the book, but we know all the steps for this, so go ahead and give it a shot. Try it if you, but the answers are right there in front of you if you decide, hey, you just want to look at them and write them down. I'd encourage you to go ahead and figure out what do we need to do now. Let's go ahead and start walking through this process. Pardon? Yeah. Yep. Well, what is the first thing we need to do? Well, what would I encourage you to do? Let's draw as much of the diagram as we can. Let's start by putting together our, solution process. We've been given a certain amount of glucose. We've been given it in kilograms. We know that this involves stoichiometry because we've been asked to relate how much of one thing when given or compared to another thing. The things we're going to compare are glucose, our C6H12O6, and we're going to compare that to H2O. How much water given a certain amount of glucose. We can only relate those things to each other not by the mass, but by their moles, right? Are we comfortable with that now? Okay, comfortable relating them. We have to relate them by moles, not by mass. That's why we kind of left the space, and now we're working on the lateral mole-to-mole ratio part of the solving diagram. And we're moving from here to there, from this reactant to that product. And we're going to have to use a multiplier, but the multiplier is based upon mole ratios of the balanced equation. Is this balanced? Well, real quick, 6 carbons, 6 carbons. 12 hydrogens, 12 hydrogens. 6 oxygens plus 12 oxygen, 18 oxygens, right? 6 and 2 is 12, plus 6 is 18. It's a balanced equation. Okay, now I'm relating glucose to water. I'm relating moles to moles because it's stoichiometry. Okay, and they relate to each other in the ratio of their stoichiometric coefficients from the balance reaction equation. So this relationship is going to be an implied 1 to 6. 1 to 6. Now I'm moving from a given or a amount of moles that I can compute to the number of moles that I'm looking for. This is my known. I may not know the number of moles yet, but I will know the number of moles. Moles from here to solve for the unknown moles of water. And so because I'm relating glucose to water, my unit multiplier becomes what? 6. I'm going to multiply by 6 to convert from however many moles of glucose relates to 6 times as many moles of water. Now I need to somehow get to this point in the diagram from here. I need to move from a mass unit, move it to a mole unit. And on that side, take it from a mole amount and move it to a mass amount. And those vertical movements are based upon molar mass. So I can put molar mass on both sides. To go from a mass to the number of moles, I divide by the molar mass. To go from moles to mass, I multiply by the molar mass. Over here, I need to divide by the molar mass of what? Here, it's the molar mass of this molecule, my glucose, right? Over here, my molar mass is going to be the molar mass of water, a water molecule. Okay. So now what we need to do to finish solving this reaction equation is to figure out the molar mass of glucose and the molar mass of water. So remember, do the molar masses. You're actually going to be adding, not multiplying. We're going to add up carbons. We have carbon 12, right? Hydrogen, 1, 2, 3, 4, 5, 6. When I said carbon 12, I meant it has an atomic mass of 12 AMUs. That's why I said 12. So I'm going to have to add up 6 12s, 12 1.01s, and 6 16s. And I come up with 180.1 grams per mole. Now, the other thing to remember is I'm not coming from 1.2 grams, right? I'm coming from 1.2 kilograms. This unit here is in grams. So make sure you put this not as 1.2 kilograms. You maybe want to consider this 1,200 grams. So make sure you multiply 1,200, take 1,200 and divide it by 180.1 grams per mole. So here's how this math would look. 1,200 grams divided by 180.1 grams per mole. And book answer says I'm going to end up with 6.7 moles. Okay? So I've taken the mass, I've divided it by the molar mass for that molecule, and I can say now that when I have 1.2 kilograms of glucose, I have 6.7 moles of glucose. And now that I've taken mass and converted it to moles, now I can apply the stoichiometric coefficient here and say if I have 6.7 moles of glucose, I have 6 times as many moles of water. Which basically comes out to be 40. I'm just going to write it as 40. Actually, they wrote 4.0 times 10 to the first, but it's 40. I'm just going to go with me on this. So 6.7. So for every 6.7 moles of glucose, I produce 40 moles of water. The question was, how many grams of water are produced? So now that I know how many moles of water are produced, I need the molar mass of water to convert my moles of water into grams of water. And the molar mass here is 18.0 grams per mole for water. So I'm going to multiply 40 times 18. And I get 7.2 times 10 to the second, which you know as 720 grams. So when I take 1.2 kilograms of glucose and I completely combust it, it produces 720 grams of water. Another way of saying it is, if I knew that I produced 720 grams of water, I could back engineer how much glucose I needed to do that. As a matter of fact, knowing this balanced reaction equation and knowing one of the molecules involved, I can solve for any other molecule in the equation, right? I mean, now that I know, if it's said, here's the reaction equation, and it does combust fully 1.2 kilograms of glucose, how much oxygen was used? How much carbon dioxide was produced? How much water was produced? I can do all of those just knowing the one element. As a matter of fact, since I know that the relationship here is 1 to 6, I can look over here to the oxygen and say, oh, it's 1 to 6 as well. Guess what? I needed to combust 40 moles of oxygen too. It took me 40 moles of oxygen. How do we know that? Because the relationship here is 1 to 6. Guess what? The relationship from here to here is 1 to 6. Oh, guess what? The relationship from here to here is 1 to 6. Here's the cool thing. I combust 6.7 moles of glucose with 40 moles of oxygen to produce 40 moles of carbon dioxide and 40 moles of water. How do I know all that? They all have the same stoichiometric coefficient. They all relate back to glucose in the same relationship. So 6.7 moles reacts with 40 moles to produce 40 moles and 40 moles. But I cannot say that 1.2 kilograms reacts to produce 720 grams. So that means 1.2 kilograms plus 720 grams produces 720 grams and 720 grams. That is not true. I can only do it on the count. I can only do it in the piece. So I could do it in terms of a molecule, in terms of a dozen, in terms of a score, or in our case, in terms of a mole. And then based upon the molar mass of the molecule, convert the moles into grams. Isn't this great? This really is cool stuff. I'm sorry if you don't think it is. It is. You're wrong, okay? Anyway, before I continue racing it, I know yes, sir. Some more stuff? Yeah, I'll delay for a moment. Sorry I raced this already. Hopefully you had that.